Hello viewers. In the last video we have discussed about the basic concepts of fractals. Today we are going to discuss about fractal dimensions. So we know that fractals are geometric shapes that exhibit self-similarity. This means they appear the same at any scale of magnification. The concept was introduced by Benoit Mandelbrot in 1970s, and they challenged traditional Euclidean geometry by possessing non-integer dimensions such as the Hausdorff dimension. So let us begin our journey into fractal dimensions where the ordinary rules of geometry bend. So these are some images of fractals. So this is the surface of a mountain as modeled by a fractal. It can be noted that any part of a mountain itself looks like a mountain. This is another fractal figure known as Sierpinski triangle. It is a self-similar fractal introduced by Polish mathematician W. Sierpinski in 1915. These are some more interesting fractal images. The first one is series say AN and another one is the fractal series AMN. This has been obtained from circles. To illustrate the concept of fractal dimension, we will explore some examples that are known such as Cantor Dust and Sierpinski Gasket. Cantor Dust starts with something as simple as a line, but ultimately it transforms into a scattered set of points. We'll also examine the Sierpinski gasket, a triangle that continuously unfolds into smaller and smaller copies of itself. In the last YouTube, we have seen that the dimension d of the object shows up as an exponent of r in the relation between n and the similarity ratio or a scaling ratio. N is the number of equal subunits and similarity ratio or a scaling ratio is r, and we get n r to the power d is equal to 1. The configuration line, square and cube have integer dimension d of 1, 2 and 3 respectively. That is, for line, this equation is obtained as nr to the power 1 is equal to 1. For square, we get nr to the power 2 is equal to 1. And for cube, we get nr 3 to the power 1. The explicit form of d in terms of n and r is found by taking the logarithm of this equation. So if we take the logarithm of both sides and simplify a bit, we get d is equal to log n by log of 1 by r. Here the value of dimension d is independent of the base of the logarithm. We can, however, envisage a situation in which there is a distribution of points for which the parameter d, which we call dimension, turns out to be a fraction. We call such distribution of points as fractals. In what follows, we will illustrate fractional dimension through well-known examples. So let us first take the case of Cantor set. It is also called Cantor Dust and we denote it by C. The Cantor set is named after George Cantor. In 1883, he wrote about it to demonstrate that the sets of real numbers are uncountable. It can be constructed following a very simple rule. So let us take a line segment A0. Let us trisect into 3 equal segments and remove the middle 1/3 of the line segment. In this way, we have the fractal A1 at level 1. On the next step, what we do, we again remove the middle 1/3 of each of the 2 remaining line segments A1 to get the fractal A2 at level 2. It can be seen through the figure shown here. At level 1, from A0, we have removed the middle 1/3. At level 2, we have removed the middle 1/3 of each of the 2 remaining parts to get the level 2. So repeating this process ad infinitum, we get a sequence of sets, say an. So what is C? C is equal to limit n tending to infinity an, and it is intersection of n equal to 1 to infinity an. C is called Cantor set, which is uncountable and totally disconnected. So let us assume that A0 is of unit length. Then since 3 into 1 by 3 to the power 1 is equal to 1, so dimension of A0 is equal to 1. After removing the central 1/3 part of A0, 2 parts remain, each 1/3 of the original one. So let us define d by 2 into 1 by 3 to the power d is equal to 1. At level 2, 4 parts remain, each 1 by 3 square of the original one. Hence d for this level is given by 4 into 1 by 3 square to the power d equal to 1, or equivalently 2 into 1 by 3 to the power d equal to 1. It can be verified that the number d is independent of the level. D is known as Minkowski dimension of the fractal. Now, from the equation 2 into 1 by 3 to the power d is equal to 1, d can be explicitly obtained as dimension d is equal to log 2 by log 3, that is equivalent to 0.6309. Thus, Cantor set is a self-similar fractal having dimension d, that is given by 0.6309. So if you try to find out the length of the deleted line segments, we will be getting interesting results. So the following arguments can be used. The length of the first interval that we removed was 1 by 3. For construction of A2, we removed 2 intervals, each of length 1 by 3 square. For A3, we removed 2 square intervals of length 1 by 3 cube and so on. So, sum of the length of the deleted line segments will be sum of all these, that is equal to 1 by 3 plus 2 times 1 by 3 square plus 2 square times 1 by 3 cube plus and so on 2 to the power n minus 1 by 3 to the power n plus it may go up to infinity. So we can take out 1 by 3 common, and we are getting 1 plus 2 by 3 plus 2 by 3 square plus 2 by 3 cube plus and so on. So this comes out to be 1 by 3 into 1 by 1 minus 2 by 3, where we are using the formula for sum of a geometric progression. So if we have the geometric progression, infinite series, sum of the infinite series S infinity is given in terms of A by 1 minus R, where A is the first term and R is the common ratio, means it is Tn by Tn minus 1, means ratio of the nth term upon n minus 1th term. So we see that sum of the length of deleted line segments comes out to be 1, and that is the same as the length of the original line segment. So measure of Cantor set is 0. However, C has as many points as A0. Next, let us take the case of Sierpinski gasket S. Sierpinski gasket is a self-similar fractal introduced by Polish mathematician W. Sierpinski in 1915. It is constructed by taking an equilateral triangle C0 of unit area. On joining the midpoints of the sides of the triangle, it is divided into 4 equal equilateral triangles with area half a square. So, we know that the area is measured by half length into height, base into height. So, base and height of all these 4 triangles are half of that the original triangles. So, it is divided into 4 equilateral triangles with area half a square. So, 4 into 1 by 2 to the power 2 is equal to 1. So, that dimension of C0 is equal to 2. If the central triangle is removed, we get the fractal C1 at level 1. In the next step, we remove the central triangle in all the remaining 3 triangles. So, repeating the process for each of the 3 remaining small triangular regions, the fractal C2 at level 2 is obtained. So, in this way, we continue the sequence of configuration. Cn is obtained, whose intersection gives the final gasket S. So, limit n tending to infinity Cn is equal to intersection of n is equal to 1 to infinity Cn, and that is the gasket S. So, what is the dimension of Sierpinski gasket? It can be obtained following the following argument. At each level, the number d for calculating the dimension can be given by 3 into 1 by 2 to the power d is equal to 1. Hence, the dimension d of the Sierpinski gasket S is d is equal to log 3 by log 2, that is equal to 1.5850. We can also see that sum of the area removed will be 1 by 4. In the next step, 3 into 1 by 4 square. In the next step, we remove 3 square into 1 by 4 cube. Plus on the nth step, we have 3 to the power n minus 1 by 1 by 4 to the power n. So, following the same rule, we first take 1 by 4 common, and then since the series, for the series we use the same formula, and we are getting 1 by 4 upon 1 minus 3 by 4, that is equal to 1. So, sum of the area removed is equal to area of the original triangle. Therefore, the set S has 0 area measure. Hence, the set S has 0 area measure. This makes S a perfect gasket in the sense that it separates its complement into infinitely many triangular regions without using any thickness. So, this is to show that the fractional dimension of Sierpinski gasket is equal to 1.5850. We have also seen that in case of Cantor dust, the dimension is fractional. So, thank you for listening. In the next class or in the next video, we may be discussing about some more interesting known fractals first of all, and after that in the coming videos we may know about some applications of fractal. So thank you very much.